Welcome. Good morning. We are in the domain of multivariate inferential statistics. Today's lecture is on simultaneous confidence interval and hypothesis testing. We continue a maximization lemma which we have started in the last class. Then we will show you one example. Then we discuss another method for simultaneous confidence interval called bound-Ferrani approach. We further discuss hypothesis testing, single population mean vector, followed by an example. Let's go to the next slide.
We will continue that our maximization lemma to find out the simultaneous confidence interval, this one. What I told you that this quantity, that A transpose x bar minus this one, if you select something like this for A, you will get like this, and which is basically like a univariate interval, and your problem will lie here that you will not get simultaneously 90% or 95% confidence interval. You require some modification, and that modification is given here by using maximization lemma, that z square n x bar minus mu transpose, and this quantity follows chi-square distribution. Now, with this modification you write the earlier equation. What have you written earlier? You have written A transpose x bar minus z alpha by 2 and this less than equal to this less than equal to this. So, this z alpha by 2 will be replaced by square root of chi-square p alpha. What sign? You see this one, A transpose x bar minus chi-square of this square into this variability component, then A transpose mu less than equal to A transpose x bar plus the same thing. What is the problem? Paper also same thing I have written. This minus this less than equal to this less than equal to this plus this. This is plus. Okay. So, what this change is like this, A transpose x bar minus root over chi-square p alpha, then the same thing you write A transpose this divided by n less than equal to A transpose mu less than equal to A transpose x bar plus again you write that chi-square p alpha, and same thing that A transpose this by n. Now, if you select A similar manner, then your individual confidence interval will be x bar minus chi-square p alpha square root of again s j j by n less than equal to mu j, this will be mu j less than equal to x j bar plus chi-square p alpha square root of s j j by n. This is the interval simultaneous confidence interval for x for mu j, simultaneous confidence interval for mu j, and if you change j equal to 1 to p, you will be getting for all other variables what is the confidence interval. Okay. It seems very difficult or easy. So, when you read that book, you read in this the approach what way I am presenting here, otherwise if you will find it very boring. At the first time when you see Johnson and Wichan, you will find that I will never read this book, and that is the purpose of this class, purpose that I am making it as simple as possible, so that you all feel reading that, please. Okay. So, now the three scenarios we have seen earlier. You tell me, are you facing problem here? Simultaneous confidence interval, scenario 1, sigma is known. So, as sigma is known, you are using sigma jj, because if sigma is known, it is better to use that sigma. Why you will go for sample variance? If your sigma unknown and large sample size, you are using sjj, you are also using chi-square distribution. When it is small with small sample size and multivariate normal plus sigma unknown, you are using F distribution. Can you find out the confidence interval for the problem given? You develop. I am giving you 5 minutes time, although I know that 5 minutes time is very big for us, but you please develop. What I say, that you have to develop simultaneous confidence interval for the mean of the variable x1 and x2 given alpha equal to 0.05. Everything is, the answer is with you. How do you go about it? Everything is given here. You see, x1 bar is 10, x2 bar is 20, and your S11 is 40 and S22 is 100, and you require to know n minus 1 p by this quantity what will be the value. Earlier we have already seen that this quantity, the critical value is 7.51. Just you put into this equation. So, 10 minus 7.51, that square root into square root of 40 by your n is 20, less than equal to mu 1 less than equal to 10 plus this quantity. Okay. I am sure that possible, and you see that these are the intervals. Which one? Whole square root, including fp n minus p alpha, there is whole square root. Okay. So, I think right hand side find out for x1 mu1 and left hand side for mu2. This side people find out for mu1, left hand side please find it out for mu2, cross check. x1 is okay, then x2 will also be okay. So, we will go to the next slide. I hope that you all will be, you have already found out the mu 1. So, mu 2 also it is possible, not a big issue. Then what is Bonferroni approach? Bonferroni approach is different than maximization lemma. Bonferroni approach says that our sole problem is when I have large number of variables, I am not getting this one. Now, this quantity definitely is less than 1 minus alpha, because alpha 1 minus alpha is always less than 1. So, what Bonferroni says, that if we want to find out collectively 1 minus alpha into 100% confidence interval, so you tighten the individual intervals. You are getting me? Like my first variable individual interval, let it be 99% you are finding out. Then second variable also you find out the individual interval 99%. Then what will be the total? If you multiply 9.99 into 0.99, what will be this quantity? You just check, it will be also a large quantity. If my interest is to get 95.95, probably it is more than 0.95. So, you have to choose judiciously, so that ultimate this 1 minus alpha to the power p will can be like this. What I can say, it will be always like this, this should be greater than, that is my requirement. As a result, he has given a formula. He says that you can give equal weightage to each of the variables, or you can give differential weightage. So, let alpha is like this, my j is 1 to p, there are p variables, and I am giving each variable with alpha j weight, that will be alpha. What is happening here? So, you have suppose p variable x 1, x 2 to that x p variables are there. Now, this is alpha 1, alpha 2, you are giving probability value for each like this alpha p. Now, my question is this plus this plus this is alpha. If you give all variable equal weights, then this is your alpha p, then this will be alpha by p. Getting me? If you give equal weight to each of the variables, so there are p variables, your total should be alpha, you will be getting alpha by p. And what will be this alpha? That all depends on what is your 100 into 1 minus alpha percent confidence interval, and you have to check what I can say, you want to see this one. Okay. Now, let us see that using this for different scenario, what are the confidence interval. First one you take first. You see the first one, and you tell me whether you are comfortable or not. First one we have already seen that is z alpha by 2. Now, instead of z alpha by 2, you are writing z alpha j by 2, and here also z alpha j by 2. Now, if you give equal weightage, then this will be z alpha by 2 p, z alpha by 2 p, when your this condition satisfied. This condition satisfied, this will be z alpha by 2 p, this will also be z alpha by 2 p. So, here you are using z, here also you will be using z, but here your sigma is unknown, large sample size, your s will replace that sigma, absolutely no problem. Third one, instead of f, you are using t distribution. Okay. So, my request to you that chapter 5 of Johnson and Wilson you please go through and see that this derivation as well as whatever explanation given there, if there is any problem please report to me. Okay. Then what is essentially the difference between Bonferroni and this approach, maximization lemma? Which one is easier to you? Bonferroni? Easy way, you just divide the total alpha to different variables, collectively the sum will be alpha. Now, there is a problem. Example 4, consider the example 3, obtain simultaneous confidence interval for the mean. So, T n minus 1 alpha j by 2, that is 19.0125. How we have got 0.0125? Because our alpha is 0.05, then there are two variables, then alpha by 2 is 0.025, again the two tailed. So, further divided by 2, you are getting 0.0125. This value is this, and once you put into this equation all these values, you will be getting 6.45 less than equal to mu 1 less than equal to 13.55. So, I am writing this 6.45 less than equal to mu 1 less than equal to 13.55. Using maximization lemma, what was the interval we got? 6.12, 6.12 less than equal to mu 1 less than equal to 13.88. Okay, there is little difference. There is little difference, almost this one 6.12 mean this one is less than this one is more than this. So, little difference is there, that difference will always be there, because you are using different alpha values and different, here it is T distribution, there it is F distribution. Now, hypothesis testing, this is the last topic today. What is hypothesis? I told you in the last class, yes or no? That is yet to be proven. Any statement, and definitely it should be a good statement, it is not that I am going there, you are also going there, this type of statement, scientific statement. Any scientific statement that is yet to be proven, that is your hypothesis. And you have seen hypothesis in univariate case also. Now, in multivariate case, what will be your null hypothesis? When you are talking about single population, that related to mu we are talking about. So, mu equal to mu 0. What is my alternative hypothesis? Mu not equal to mu 0. Okay, very simple. What is this mu? This is mean vector. Please remember, whenever we are writing like this in multivariate domain, although we are writing mu, many a time you commit mistake. You think that okay, this is 1 mu, that scalar quantity, it is not like this. So, in hypothesis testing, the steps are find out the null hypothesis and alternative hypothesis, that is your step 1. What will be your step 2? What I have given you in univariate case? You have to find out the appropriate statistic. So, find out appropriate statistic. Then what will be your third step? You must know the sampling distribution, know sampling distribution of that statistic. Then what is the fourth step? You definitely compute the value of the statistic. From sampling distribution of the statistic, you find out the critical value. Then your step 5a, compare the computed statistic value with the critical value, obtained from the statistical table, you will use table, an appropriate statistical table. Then your step 6 is make decision. What will happen if your computed statistic is less than the tabulated value? Null hypothesis cannot be rejected. So, decision is reject null hypothesis H0 if in this case we are saying t square that computed is greater than that particular tabulated value. You have to see that what is this t square tabulated value. It all depends on the distribution. If it is chi square, then you have to use the chi square value here. If it is F distribution, go for F distribution like this. Okay. See this slide. Your first scenario chi square distribution, and this is the case reject H0 if this quantity is greater than chi square p alpha. See, already you have computed all those values. In the earlier example, you have computed this value also, you have computed, I think that this value you have not computed, mu 0 is given now. Okay. One of the issue here you must remember that whenever we are talking about sampling distribution of a statistic like this t square is this, we are saying that when null hypothesis is true, this statistic follow this sampling distribution. Please never forget this one. Okay. So, if you change your null hypothesis to something like this, that mu less than mu 0, then you will not get the appropriate distribution because it is not developed. Maybe developed, we do not know. But what we know here that our null hypothesis is mu equal to mu 0, then only this quantity t square, this is chi square distributed, where t square is this, where sigma inverse is there. So, please do not change your null hypothesis. Actual means there are two hypotheses in this case, null and alternative hypothesis. Null hypothesis is someone which it is a statement which is not yet proven, that hypothesis you were talking about. Okay. There is no actual hypothesis, something like this. It is basically, it is a proposition, you do not know what is the true things, you are trying to prove it based on data analysis. Okay. So, there are two hypotheses, null and alternative hypothesis. In case of population, your scenario 2, your state statistic is this, distribution is this, and reject like this. So, do not look at the equations, you just think the message what I am giving you, that is more important, because whatever given to you, ultimate aim is few things that must be remembered by you. One is what is your random variable. For example, x bar is also a random variable. Then you are creating certain statistic using appropriate statistics using this random variable this is also a statistic, but for finding out the same distribution you may not get distribution of x bar, you may get distribution of something else. Here x bar distribution is also available, but for computational purpose we are converting into z or t square or something like this. Then you must also know the distribution of this statistic, here it is distribution of t square, and then you have to find out that what are the value, and this is the steps, whether it is t square distribution, z distribution, chi square distribution, t distribution, all cases things to be followed exactly the same. So, do not forget that these equations may be big, but these equations are no way hampering your understanding. Okay. Then scenario 3, you all know that you will be using the sampling distribution f. So, again your decision will be like this. Now, if this is the case, then see one problem again. Consider example 4, conduct hypothesis testing for population mean vector mu 1 equal to 9 and mu 2 equal to 18, alpha equal to 0.05. See, x bar is given, mu 0 is given. What is your null hypothesis here? Mu 1, mu 2 equal to 9 and 18. Okay. So, you write down this x bar is 10, 20, the same problem I am discussing, that mu 0 is 9, 18 and s 40 minus 50 minus 50 100, and this is the calculation. I think you all know that we have already found out that t square is 1.33, 10 minus mu 1 will be mu 10. So, mu 10 square 1.34, 10 minus mu 10, 20 minus mu 20 plus 0.53, 20 minus mu 20 square. What we have found out, that mu 10, this one is your 9, mu 20 we have found out it is your 18. Put into this equation. If you put into this equation, this is 1.33, 10 minus 9 square, 1.34, 10 minus 9 into 20 minus 18 plus 0.53, 20 minus 18 square. You are getting a value 1.33 cross 1 square, that is 1, plus 1.34 into 1 into 2 plus 0.53 into 2 square, that is 4. So, what will be this value? 1.33 plus 2.68 plus 4 into 3, 12, 2.12. So, this is 6.13, correct. So, this is what is computed t square computed from data. What is your tabulated value? We say it will follow n minus 1 into p by n minus p, f p n minus p, and you have to find out some alpha value. Alpha is 0.05 like alpha. So, that we have already seen that 19 into 2 by 18, f 2 18, if we write it 0.05, this resultant quantity is 7.51. So, reject yes or accept. Why reject? Huh? You will accept or reject? If t square computed is greater than equal to t square tabulated, then reject H0. So, our computed one is 6.13, is it greater than equal to 7.51? No. So, our decision is fail to reject H0, fail to reject H0. Mu equal to mu 0. No, your null hypothesis H0 mu equal to mu 0. What we are saying then? Suppose I have written 0 like there, basically mu 1, mu 2, that 0 stands for null hypothesis, that is this one is 9 and 18. This is your null hypothesis. what you have x bar equal to 10 and 20, and you have s that is what is 40 minus 50 minus 50 and 100, and now you know what is the population characteristics, and based on this t square computed, t square tabulated, both is computed, and you see, if you see this value, what is x bar 10 20. Now you are creating one hypothesis, null hypothesis like this, mu 1 0 and mu 2 0, this just to give this 0 notation here, 9 and 18. So, 10 minus 1 20, only 1 and 2 that difference, x bar minus mu 0, that difference is 10 minus 9 is 1 and 2. The statistics based on this sample covariance matrix, when you are computing like this, you are not finding out this one is similar to 0 0. Getting me? That difference what you have assumed and coming, there is not much difference. Actually, what is required to know here, your chi-square, I think we have taken f distribution, this is f value, this is your distribution. When you are taking alpha value is 0.05, this is what we are getting here 7.51, and your value is coming somewhere here 6.13. It is within this interval. You cannot reject the null hypothesis. Okay.